Episode 36, Analyze Code to Uncover Latent Security Risks, we focus on turning ordinary code reading into a deliberate method for finding problems before attackers do. Most security issues are already present in the code long before they show up as incidents. They just hide in patterns that everyday reviews do not always highlight. When you adopt a structured way of reading, you stop scanning for style and start following risks, flows, and assumptions instead. The aim is not to make you a full-time auditor, but to give you a repeatable lens you can use whenever you touch a codebase. With that lens, each review becomes an opportunity to uncover latent weaknesses and shape safer designs. A focused code assessment starts by establishing scope, trust boundaries, and critical data handling entry points. Scope describes which modules, services, and interfaces you are examining, so the review does not diffuse into the entire system at once. Trust boundaries mark transitions between internal and external callers, between internal privilege levels, or between zones with different protection expectations, such as public endpoints, internal services, and administrative surfaces. Critical entry points include API handlers, input parsers, message consumers, and file or batch processors where untrusted data first lands. When you have this map in mind, you stop reading line by line and instead move with purpose from boundary to boundary. Once boundaries and entry points are visible, the next step is tracing data flows, especially following tainted inputs through transformations and into sinks. Tainted data is anything that originates outside the trusted core, such as user fields, headers, query parameters, message payloads, or file contents. As you read code, you follow how these values are validated, normalized, and passed along, watching for places where they reach dangerous operations like database calls, command execution, template rendering, or file system access. Each transformation becomes a checkpoint where you ask whether the input is constrained, encoded, or left untouched. This mental tracing often reveals subtle paths where untrusted data quietly reaches powerful functions. Authentication, session handling, and privilege escalation logic deserve special attention because they shape who can do what and under which identity. When reading authentication paths, you look for consistent verification of credentials, safe storage of tokens, and careful handling of failed attempts or lockouts. Session handling involves checking how session identifiers are generated, stored, renewed, and invalidated, as well as whether they are bound to context such as device, client type, or location. Privilege escalation checks include patterns like role changes, temporary elevation, or administrative operations hidden behind weak conditions. Code that handles these areas is often compact but high impact, so reading it with skepticism and patience pays off. Cryptography usage is another rich area for latent risk, so you inspect algorithms, modes, keys, nonces, and randomness with care. Code that calls encryption or hashing functions should use modern, recommended algorithms and avoid weak or obsolete choices that linger from legacy implementations. Modes of operation must be appropriate to the use case, since a strong algorithm with the wrong mode can still leak patterns or be vulnerable to manipulation. Nonces, initialization vectors, and random values should be generated using secure sources and never reused improperly. As you read, you ask whether cryptographic decisions match current guidance or appear improvised and fragile. Error handling, exceptions, and logging can either reduce confusion or quietly leak information, depending on how they are written. When you inspect these areas, you look for catch blocks that swallow errors without recording enough context, as well as ones that log too much detail, such as secrets or internal system layouts.
You also examine how error paths return messages to callers, checking whether they reveal stack traces, file paths, or sensitive state. Logging statements deserve scrutiny for formatting, consistency, and the possibility of logging untrusted input directly. This review helps you spot places where failures could either hide real problems or give attackers a tour of the system's internals. Resource management is another recurring source of security and stability problems, so code that handles memory, file handles, sockets, and concurrency primitives deserves careful reading. You look for paths where resources are allocated but not reliably released, especially around early returns, exceptions, or timeouts. Concurrency constructs, such as locks, semaphores, go routines, or threads, can introduce deadlocks, race conditions, or inconsistent state if they are not used with clear discipline. File and socket handling code should show predictable open, use, and close patterns, as well as timeouts and safeguards against uncontrolled growth. Latent security risks often appear here as availability issues, data corruption, or opportunities for denial of service behavior. A targeted code audit also looks for insecure defaults, hidden flags, or debug-only shortcuts that remain available in production paths. Insecure defaults might take the form of permissive configurations, broad access scopes, or optional security features that start in a relaxed mode. Hidden flags may enable verbose logging, bypass authentication checks, or disable throttling and rate limiting when toggled, yet remain poorly guarded. Debug shortcuts can be as simple as special headers, magic values, or unadvertised endpoints that developers used for testing and never removed. As you read, you take note of any branch that says temporary, debug, or to do, and ask whether the surrounding safeguards are sufficient. Comparing implementation against standards, patterns, and declared requirement constraints helps you see where code has drifted away from intent. Requirements may specify cryptographic strengths, access control boundaries, or logging behaviors that the code only partially enforces. Standards and patterns, such as secure coding guidelines or architectural reference models, offer a baseline for what good should look like in a given stack. When you see code that deviates without explanation, you treat that as a prompt for deeper investigation rather than assuming it is harmless. This comparison anchors your reading in written expectations rather than personal taste. Static analyzers add another dimension to your review, but they work best when you use them deliberately. Tools that scan code for known patterns of vulnerabilities or bad practices can surface issues you might miss during manual passes, especially in large or complex modules. Tuning rule sets to your context, suppressing findings only with clear justification, and triaging results based on real risk rather than mere count turns these tools into partners instead of noise generators. As you review analyzer output, you correlate findings with your own observations, treating overlaps as higher priority and isolated, low-risk items as candidates for later cleanup. Areas that look risky on paper warrant targeted unit tests and, where feasible, property-based checks to validate behavior under varied conditions. Unit tests can focus on boundary cases, malformed inputs, error paths, and unusual sequences that might trigger unexpected behavior. Property-based testing, where you define invariants and generate many random inputs, can reveal surprising edge cases that no one thought to write by hand. When you add tests to code you have just examined, you create a bridge between static reasoning and dynamic evidence. This practice gives you more confidence that the risks you identified are either confirmed and addressed or shown to be under control. As you find defects and risky patterns, recording them carefully with evidence, severity rationale, and remediation recommendations is crucial.
Evidence might include specific code snippets, stack traces from reproductions, or test cases that demonstrate the behavior.
Severity rationale explains why the issue matters, referencing impact, likelihood, and environmental context rather than relying on vague terms like serious or minor. Remediation recommendations should point toward concrete changes, such as adopting parameterized queries, tightening validation, or aligning with a known secure pattern. Well-documented findings make it easier for teams to act and for future reviewers to understand what has and has not been addressed. Viewed as a whole, this approach to code analysis covers a consistent set of themes. You map data flows, examine authentication and session paths, scrutinize cryptography, and look closely at error handling and resource management. You augment manual reading with static analyzers, guard against insecure defaults and debug shortcuts, and align code with standards and requirements. You validate suspicious areas with tests and then document findings in a way that connects risks to actions. Together, these steps transform code reading from a vague, looks fine exercise into a targeted, repeatable risk discovery practice you can trust. To turn this into an immediate habit, choose one module or component you know matters to your environment and deliberately schedule a focused review session for it. In that session, start by sketching its scope and trust boundaries. Then pick one or two flows to trace from entry point to sync. As you read, jot down potential issues and mark areas for deeper testing or analyzer configuration, resisting the urge to fix everything in your head without evidence. Afterward, capture at least one or two concrete findings with clear descriptions and suggested changes, even if they are modest. Each review of this kind adds to your skill and gradually raises the baseline security of the systems you work on. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.